So I'm Jim Moawad. I spent the first portion of my career designing hardware with processors and FPGAs. At the time, the processors were PowerPC processors. That might date my career a little bit because ARM didn't really wasn't as ubiquitous as it is these days. And then in 2006, actually, I came to this campus for what they called Altera Boot Camp. And for a really good chunk of the remainder of my career, I've been supporting Altera FPGA designs. And for the last about 5 years, I've been a tech specialist focused on edge compute, helping customers with all kinds of things, including a lot of conversations about how to get AI into FPGAs. And so maybe you were in this room for the previous two sessions, maybe not, but there were a couple of previous sessions about the FPGA AI Suite. And I've talked to lots of customers about using the FPGA AI Suite to get a lot of heavy compute into the FPGAs. What we'll talk about here is kind of the other end of the spectrum a little bit. Okay, so we'll go through that. And our agenda for today is to talk about an industry term that's come up, I don't know if you've heard it, called TinyML. And then we'll talk about how we can use that concept across Altera's offering. And then we put together a design, and it's documented in a white paper, and we'll show you some latency numbers so you can see how, what the different options are and how they compare. Okay. So I've got a fun game for you here. You can scan that QR code. I should probably get out of the way so you can scan it. And the question I want you to answer is, if I say TinyML, what comes to mind? And this will create a little word cloud. We can look in and see what you come up with. But TinyML, maybe you've heard that term. If so, what does it mean to you? And if you haven't heard the term before, it's the first time you hear TinyML, what does that phrase, put in your mind? Okay, so we'll see if you can come up with maybe some attributes or something like that of where TinyML, what that says for you. Okay? Good, looks like we're getting some decent results here. Yeah, there we go. There's a lot of good adjectives I'm seeing there. Optimized, small model, compact, low level. Okay. I see a competitor product, Jetson Nano, but that fits maybe some of these descriptions too. So yeah, these are some good words I'm seeing popping up. Okay. With that, we can go back to the presentation, and I'll give you a definition. Okay, so this term is a little bit of a vague term, and there's not exactly clear definitions. I've seen different definitions out there. But we'll just say that TinyML is using machine learning models on low power, low resource devices, microcontrollers and small scale processor type devices. And we've got 4 pillars up here that we're going to talk about. So we want it to be resource efficient. Okay? So resource efficient, meaning like we want to be able to use the types of processors and things that are really at the very simple end of the spectrum, the lower power, more simple end of the spectrum. Okay. TinyML is also helpful in keeping power consumption down. Obviously, if it's something battery operated, that would be really useful, but not just for battery operated applications. It's really useful when you've got thermal challenges. All kinds of things become easier when you're using less power. Okay. So if we can keep thermal challenges down, make power supplies simpler, all those kinds of things, that's better too. So that's another one of the goals of TinyML, is to keep power consumption down. And then the last 2 pillars there are both driving a push towards getting machine learning and deep learning models happening like at the edge in the device. So one of those things is real-time processing. If we want things to be a little bit more real-time, then one good way to achieve that is to have it happen in the device, rather than to ship the processing to happen somewhere else, on some rack of servers or in a cloud somewhere. Right? If we can just do it on the device, that cuts out a lot of transport time and can make things a lot more real time. Similarly, privacy and security is also driving the shifting things towards being in the device. It's much simpler to keep your data and information secure if you haven't shipped it anywhere, if you're doing the processing right there locally on the device. So that's another big benefit. Not to mention that our Altera devices have a lot of security features that can really help with that as you're securing it on the device. Okay, so I want to point out something that maybe is obvious, maybe it isn't, but when it comes to deep learning models, there's a really big range of what kinds of compute they need. And this chart here is showing just different standard models that are in the big category. There's a big category of deep learning models called convolutional neural networks, feed-forward convolutional neural networks. And these are some of the standard ones that have been out there for a while. At the top of the chart, you see something called VGG. It's a pretty compute-heavy model. And then there's some, maybe you've heard of ResNet. ResNet's, one that's mentioned a lot. It's used for imaging tasks. And there's different flavors of ResNet. You can see those towards the top, down into the middle. And then at the bottom, there's a much simpler model, LINET. We'll actually walk through that a little bit because we have a white paper that I'm going to go through where we've built up things using LINET. Okay. And all these models tend to be used for tasks of processing usually 2D data. So image data, maybe radar data, something like that. But it's usually 2D data that's being processed. So any of these models are used for that kind of task. But they range quite a bit in how much compute they have. And of course, maybe in what kinds of problems they could solve in terms of processing that image data. But there's a really big range of how much compute's needed here. That model at the bottom of the chart, LINET, when you compare that to VGG, that's a compute difference of 2000x. So if you can get things to operate with a model at the bottom of the chart, that's a lot less compute we have to worry about. So that's what we're talking about when we get into this term TinyML. When it comes to the Altera portfolio, we have a very scalable portfolio of products. Starting with the FPGA devices, we've got not only FPGA devices that are very capable of doing a ton of compute. Agilex 7 type FPGAs have thousands of DSP blocks in them. So you can really put a ton of compute in those. We also have simpler FPGAs that still have nice hard floating point DSP blocks, but maybe not quite as many. So there's that whole big range from Max, Cyclone, Aria, Agilex, Agilex 7, Agilex 9, Agilex 5. There's a whole big range of FPGA devices. So there's a lot of scalability there. But also, if we just think of processing on the processor side of things, we also have a lot of SoC processors where we can do some compute. And we have the ability to put in a soft processor with the Nios V, which is a RISC-V instruction set architecture. We can put that into our FPGA fabric as well. Okay. So those are all options. And today with TinyML, we're going to focus on these right two things, which is, what if we just run these models, a simpler version of models, on the processor itself? Okay. And so when it comes to implementing AI in our devices, there were the previous sessions talking about using the FPGA fabric for FPGA AI Suite. Great. If you need a lot of compute, that's a great way to do it, absolutely. But what we'll talk about here is we can use the ARM SoC to run AI inference. And the ARM is a pretty capable application class processor. We can also use the Nios V, and if a model's simple enough, we can run Nios, that model on the Nios V soft processor just as well. Okay. And that's actually a good option to keep in mind because maybe you're using one of our devices that isn't an SoC device. Or maybe you've already got all kinds of things running in your, on your ARM processor, and you just want to keep this task separate. You could put it on a Nios processor in the FPGA fabric and keep it separate. So that's something to keep in mind. Okay, so before getting into showing how we implement and get a deep learning model application into our devices, I'll just back up a little bit and talk about how models are trained. In one of the earlier sessions, Audrey talked a little bit about this. We'll kind of review and maybe show a slightly different angle. But the idea here is that a deep learning model is a topology where you've got a bunch of information that can be processed through it, but something has to determine what all the weights are so that the model can do some nifty task. And the way that happens is by doing data science work, which means we need to come up with an idea, In our case, our idea is going to be handwriting recognition. So we're going to walk through an example of looking at digits, handwritten digits, and recognizing what those digits are. So that's our idea. And so in order to get a model to be trained up to do that, we need to come up with a data set. So we'll have a data set, and in the case of this example, that data set would be a bunch of images of handwritten characters that are labeled. All these different examples of handwritten 2s, those are all 2s. All these examples of handwritten 5s, those are 5s, and so on. And then those are trained on different models, and the model will crunch on those and converge and come up with weights that can work. And then you can run then against like a test data set and then also a validation data set to see, like, is this model actually working on stuff that it wasn't trained on to do that task well? So that's like the really brief overview of how the models get trained. Of course, that's a whole science on its own. We're not really going into all the details there, but just wanted to point out that that work needs to happen. And when that happens, you can do this training process on different models and see how each model performs. And so once you have a model that you like, it seems to perform well. If it's a nice, simple model, maybe that fits in the realm of TinyML, and we'll see how to get it deployed and put onto a device. So the question then is, okay, how do we get a model into a device, and how do we do that in a fashion that can be run on small, simple microcontroller type devices? Well, this slide here is basically a replica of something found on the TensorFlow website. They have a process called TF Lite, where you can get a model to be run in a much simpler fashion. So TensorFlow is a tool that is used for model training. And once you've trained up a model in the TensorFlow tool, they have a process to create a lightweight version of that model that's meant for simple devices. So the way that works is you can take a trained model and push it through what they call the TF Lite converter. And then you get a TF Lite version of the model. Okay. And you can start with either a model that you've trained yourself. They do also have pre-trained models. So that's another option, is maybe you're not going through that process of training the model yourself with your own data set. Maybe you grab a pre-trained model. Maybe there's a model that is pre-trained to differentiate between people, bicycles, and cars, or some other task, and there's some pre-trained model. That's an option too. They do also have some models that are off-the-shelf pre-trained already in the TF Lite format. So those are all things that you find on the TensorFlow website. Okay. And so that's the part of the process that we're going to talk about, and then we're going to talk about how to get that into our devices, our processors and our devices. And that's done with the TF Lite micro library. So there's a set of libraries that are used so that you convert your model into a TF Lite version of the model, a TF Lite C++ version of the model, that then calls these TF Lite micro libraries so that it can run on small, simple processor type devices. Okay. So what we've done, and we put this together in a white paper, is we've trained up a model. We use an MNIST data set of labeled characters. We trained up a Linnet 5 model. By the way, Linnet is a model that's been around a really long time. It's from the late 90s. It was developed by some folks at Bell Labs. The main guy on the paper, his name was LeCun. I think that's where the name Linnet comes from. And it was famous for being used by the US Postal Service as the model that they used to implement recognizing handwritten zip codes. So this is a model that was proven and has been in use for a long, long time. And so it's still a nice, useful, and the good thing about it, in our case here, when we're talking about, are there some things that can be done in a simple fashion? This is a nice, simple model that doesn't use a ton of compute. Okay? There's still a fair amount of math there that needs to happen, but we can do that math in some of our processor-type devices. And so we trained up a model, a Linnet 5 model, with this data set that we got from MNIST. And then we pushed it through the TF Lite converter. And then double check that it still works correctly. And then convert that into a TF Lite C++ model. Load up the libraries so that we can run that on either the Nios V soft processor or on the ARM hard processor. And in the white paper, we specifically use the ARM, the Cortex A55 that's in the hard processor system complex of the Agilex 5 devices. Okay. And then the bottom portion of this slide is really talking about how at some point we've got to configure those processors, whether it's the ARM hard processor that gets configured inside of a tool within Quartus called Platform Designer, or similarly for Nios. I guess maybe I'll pause and I'm just curious, who here has used Platform Designer? Yeah, okay, it's a fair number of hands. That's kind of what I was expecting. Long-time Altera folks are probably familiar with that. If you're a really long-time Altera person, you may remember previous names like QSys or even before that SOPC Builder. This is all an evolution of a system building tool that's been around a long time, but that's what's used to assemble and configure either a Nios 5 soft processor. You can instantiate that processor there and connect it to peripherals, or if you're using the ARM hard processor, you also use Platform Designer to set it up, that processor configuration and connect it to various peripherals and things in the FPGA fabric. Okay. And then you use Quartus to generate a programming file. Okay, so this is just an aside. I'm showing a screenshot here because I mentioned pre-trained models. I just wanted to point out an example of one off the TensorFlow website. So this example here is showing they have a pre-trained version of MobileNet V2. MobileNet V2 is a standard model that's been around for many years, and they have it pre-trained with the ImageNet database. ImageNet is a data set with over 1 million labeled images that fall into 1,000 classes. So they have classes like car, wine glass, clock, person, tennis racket, teddy bear. I've had a demo in the past, I don't know if any of you have seen it, where I show off, recognizing my tennis racket and teddy bear and things that I have. So that's this pre-trained model. Just wanted to point that out. And they have many others there up on the site as well. Okay, so back to the demo that we put together, this TinyML demo. I'll show you a short recording of it where we're running this handwriting recognition app, this character recognition app. And what you're going to see here, I just described what you're about to see, which is the terminal output of the application. And so what the app does is it reads in images, which are pixel arrays of handwritten characters. And when it reads those in, the app actually outputs back out of the terminal an ASCII art view of what it's read in. So you'll see that scrolling on the screen. And then after each image is read in, it guesses which digit it thinks that is and spits that out as the output. Okay? So you can see here, it reads in various images and it's showing you what it's read in. This is an ASCII art representation. And then after it reads that in, it shows the scoring. This recording here was from the Nios 5 processor. Same thing we have running on the ARM hard processor as well. It runs a little faster there. And I'll show you a little blow up here so you can see what I'm talking about with the inference results. So this is the result of its inference. It gives a scoring for each of the different classes. Each of the classes it's making is one of the digits, 0 through 9. And in the case of that last image that it read in, it thought that image looked like a 9, at least it had a 99.4% confidence, right? So it's showing you the confidence level for each of the classes there. So it thought that what I thought looked like a handwritten 9, it also thought was a handwritten 9, and it has a confidence level of 0.994. Okay. On the Nios 5, this takes a little bit under a second to run, 0.829 seconds. On the ARM hard processor, it's a much more capable application class processor. We can run the same application there. When we run it there, it runs in just 19 microseconds, right? 0.019 seconds. Okay. If we want to run this on a Nios 5 and having it run in a little under a second is acceptable, great. Like, this was really simple. It's just software. It's easy to do. Great. That's a great option for us. If we need to speed it up and have it run faster, there are options for us. One option is the Nios 5 does have the ability to run custom instructions that can accelerate things. So perhaps we can accelerate this with a custom instruction where we use some more logic in the FPGA fabric to accelerate some of that math that's happening. That is a possibility. Okay? Or perhaps I can just move and run this on the ARM processor. You can see the ARM processor is a nice capable processor. We can run it a lot faster on the ARM processor. So that's an option too. Basically what we're showing here is that there's a lot of options for where you can do this kind of processing. Okay, so this example that we've gone through and we've implemented and documented for you is digit recognition, handwriting digit recognition. But I'd like you guys to pull up yet another QR code. We're going to come up with another word cloud here and see. I'm curious if you have other thoughts, other ideas of what could be accomplished with a TinyML app like this. So we'll see if you guys come up with any clever ideas. Who's creative? Who's got good ideas for things maybe at this simpler end of the spectrum that could be useful to be done in a machine learning type algorithm? Okay. So we'll give you guys a minute or two to come up with ideas. And this is a little bit harder than my first question. So we'll see what you come up with. There's a couple examples I'm seeing here. Maybe we can start showing the results here. So yeah, maybe some of these could be doing, things like looking at traffic patterns, or maybe some sort of a language translation word, shape recognition. Yeah, recognizing certain shapes. That might be simple enough. The key here is if the tasks are kept, simple or maybe aren't super complex, or you're classifying into a limited number of classes, these are the sorts of things where it could be straightforward and simple enough that you don't need a lot of heavy processing, and it can be done just by the processors in our devices. Yeah, signs, race riddles. Yeah, these are good. So great. Sign language, I like that. Okay, we'll go back and resume walking through our presentation here. If you do have, some of those applications I saw there, like facial recognition, actually, we saw the example of that on the Terasic demo on Agilex 7 this morning. Some of those things, like facial recognition, maybe those become pretty heavy models. And maybe, what can be done on a TinyML model running on a processor doesn't quite encompass that. So there were already a couple previous sessions. If you were in here, you saw them. If you weren't, I just want to remind you of the option to run this in the FPGA fabric using FPGA AI Suite. So that's a really good option for you. And this is a process that, in our case here, we've been talking about TensorFlow. TensorFlow is one of the options of a tool you can start with. And you can start with TensorFlow and push it through this whole flow. It goes to an OpenVINO model optimizer to get it converted, and it feeds into the FPGA AI Suite, and it ends up in IP in the FPGA. And now you can run in the FPGA fabric very performant. So again, we've got lots of options. You can run things in a Nios 5. You can run them on the Altera processor. If you're beyond that, we can get it in the FPGA fabric and have it be very performant. We've got you covered, no matter where in the spectrum you need to be. So there are a bunch of different tools and delivery mechanisms to create a successful TinyML application in our devices. Obviously, we have the Quartus Prime software, but within that is Platform Designer, where you set up the Nios 5 or the ARM-powered processor. If you work through the white paper, we use the risk-free IDE as an IDE and debugger. It's a totally free set of tools. It supports the Nios 5, RISC-V instruction set processor. And then we have a whole ecosystem of the stuff that comes from TensorFlow, which is all open source, the TF Lite libraries, the TF Lite micro library, those things I was describing. And then if you're working with the Nios 5, that is a licensed IP core that you get from us at Altera. It's a free IP core, so we have a self-serve licensing center where you can go check out for yourself a free license to use that IP core. And there's a bunch of example designs available for that, both on the Altera FPGA Design Store and on GitHub. Okay. So at this point, I'm going to welcome Liz Chen to come join me here. We'll talk a little bit.
Hello again.
Yeah. So Liz is a senior managing director with Terasic, which is one of our long-time board partners, and she was in the keynote earlier today, so yeah. Good to have you back here.
Thank you, Jim.
Mm-hmm. Okay, so I've been working with Terasic boards myself for probably 20 years, starting with an old board called the DE2. I like that board a lot. It was based on one of the early Cyclone-type devices.
Yeah, so Terasic, we've been wearing Altera uniform date back to 20 years ago. And at Terasic, we excel at building great FPGA kits. You know, our core team members, they work in a major IC design house in Taiwan, previously like more than 20 years of experience. And we adopt the methodology of IC design to build our most robust FPGA platforms. So some professors, they even complain to me saying that the university don't grant us budget because your D2 is still working, so we don't have any budget to even upgrade our platform to like newer generations such as Agios 5.
Yeah, they'd like to upgrade, but the boards just don't want to break.
Yeah, so it's like simply too robust. That's the only complaint that we receive from the universities.
Yeah, so maybe you can tell us a little bit about the wide range of products that Terasic offers.
Absolutely. As mentioned in the opening keynote, Terasic, we offered an extensive product portfolio. We designed the enterprise-class PCIe accelerators for data center and Wall Street, such as the D10 Agios accelerator you see in the keynote. And we also built a custom design like industrial-grade SOMs and ASIC prototyping boards. For entry-level starter kit, we designed a variety of cost-friendly FPGA starter kits, such as the famous D2 and the D10 Nano, D0 Nano, which is based on Cyclone 5, and also the D10 Lite board. These two boards are like $100, so it's like very cost-friendly and cheap. And these boards, they are loved by global universities as well as the industries.
Yeah, and actually, I have that DE10 Nano sitting on my desk. I use it a lot. I also have this DE10 Agilex sitting on my desk, and you know, I like that demo you showed in the morning. I got to figure out how to get that running on my board. But, yeah.
Yeah, cool.
So maybe you can tell us a little bit more about the Agilex 5 platforms here.
Of course. So at Terasic, we offer 5 platforms based on different density of Altera Agios 5 FPGA. We have introduced Autumn A5 development kit, which was introduced earlier by Sandra in the morning, and also the D25 standard development kit. The Autumn A5 development kit is an out-of-the-box development platform for AI application. So if your workload is related to AI, embedded vision, then the Autumn A5 will be your perfect platform. The D25 development kit that you see here is the newest generation dev kit for Altera University program. And this board, developers can leverage the AI tensor block on the Agios 5 FPGA, as well as the MIPI CSI DSI connector on the D25 kit to just jumpstart your AI applications.
Great. So thank you very much for going through all of that.
Thank you so much, Jim.
Yeah, you're welcome. I need to get myself an Agilex 5 board.
Yeah.
Thanks.
Thank you.
Yeah. Okay, so that brings us to a bit of a summary point here. I think you hopefully have gotten the idea that you know, when it comes to TinyML, the idea is if you have a simple model that is pretty lightweight and can be compact, then you know, a nice, easy way to deploy that is just to keep it in software. If that's an option for you, awesome. And we've just made sure that we can validate and run those flows through our tool set and get them running on our devices, and it all works and it's documented in a white paper. So that's this QR code here. If you want to see the white paper, it's live up on the website. Feel free to look at that, and it just walks through more detail on what I briefly you know, touched on here. Okay. And this is done with no-cost tools. Everything is totally free to run this stuff. The Nios 5 is a licensed IP core, but it's free to use. And all those other tools that we showed are freely available tools. And this works on all of our devices, including low-cost, low-power devices like the Max and Cyclone series, which are awesome workhorse devices at the more entry-level end of the spectrum. And if your compute needs do grow and you have more complex deep learning models, no problem. We've got to wait for you to move up and scale up and get that into the FPGA fabric. So thank you very much.
Altera, accelerating innovators.